In this video, we'll discuss how we can use matrix to describe the simple linear regression framework. Again, for this, I don't want you to focus as much on the arithmetic as I do on the form of the equations and understanding how all these things fit together. Now, it is important to understand what we're doing with the matrices, and that's why we did this matrix review in a previous video, but it isn't going to be a main feature, and you're never going to have to do this by hand. So let's revisit the scalar form of the simple linear regression model. We have our y, beta 0, beta 1x, and then epsilon, where the error was independently and identically distributed as a normal with a mean of 0 and a standard deviation, or a variance that was constant at sigma squared. We also had observations that went from 1 to little n. Now consider writing an equation for each one of these observations. That is, instead of just writing a generic I that could be replaced with any number between 1 and n, we wrote this equation for each individual. We would have y sub 1 equals beta 0 plus beta 1 x sub 1 plus epsilon sub 1, y sub 2, beta 0 plus beta 1 x sub 2 plus epsilon sub 2, and so on until we got all the way down to the nth person. This is the idea of the first step that we're going to take in writing the matrix equations. Now, if I split these out as a series of different vectors, we would have the y vector with all of the observations from y 1 to n. We would have the what we call the fixed component, which is the beta 0 plus beta 1 x1. This is also y hat. Recall, this is the predicted y, all the way from x1 to x sub n, so the nth individual. Notice that the betas never change. They're constant over everybody. And then epsilon sub 1, epsilon sub 2, all the way to epsilon sub n, so an error vector. Now note that this error again changes for each person, though we assume that the variance in a traditional simple linear regression model is constant across all of them. Now, one of the things that we can do is we can take out, because the beta 0 and beta 1 are constant here, we can remove them and write this as a vector of 1s and then, a matrix with the first column being 1s and the second column being the x's. Now in this particular construction, if you think about what this does, if I multiply this matrix times the column vector of betas, the beta 1 gets multiplied by the from the first row gets multiplied by the first column, and the beta 0 gets multiplied by the first column, and the beta 1 gets multiplied by the second column, which gives us the same thing that we have in the first vector here. So this representation is mathematically equivalent, and again, it's because of how matrix multiplication works when we multiply our matrix by this element. Now, in looking at what this then is represented by, we have our vector of y's, our y vector, bold y, equals the matrix of x's, this is something we'll call the design matrix, times the vector of betas plus the vector of epsilons. And this is our initial matrix form. Now, y is the response vector. This is the vector of all of the different responses that we have. X is called the design matrix because actually in X, this is where all of our independent variable information is located. We have 1, which indicates that we have a constant intercept for each individual, and then we have our independent variable, which can change for each individual. Beta, the bold beta, is the vector of the parameters that we're going to be estimating, in this case, beta 0 and beta 1. And then the bold epsilon is the error vector, the vector of all of the different errors in the theoretical model. Now, once we have these components, we can start to look at some of the other components, such as the covariance. Now, the covariance matrix of the error term. Now, the error term is the only thing that varies in that particular model. So the covariance matrix for the model is the covariance matrix of the error term. In this particular case, when we're looking at the relationship between error 1 and error 2 outside of the model, we note that there should not be a relationship between error 1 and error 2. That is, our off diagonal should be 0. There should be no covariance or no relationship between the data points that's not included in our model. However, each of the epsilons are expected to vary, but they're expected to have a constant variance. So in a previous video, when we talked about the generic form of this covariance matrix, we indicated that each of the data points could have their own variance term. However, here I hope you notice that each of these diagonals, that is the variance for each of the data points, is the exact same value, sigma squared. It doesn't include any subscripts to indicate that it's for a particular data point, and this is where our assumption of constant variance comes in. So actually in this matrix we can see both our assumptions of independence through the fact that the off-diagonal elements are 0, indicating that there is no relationship between off-diagonal elements, and in the fact that our diagonal elements are all the constant sigma squared. Now this can be summarized by sigma squared times the identity matrix, the n by n identity matrix. Note that the covariance of the y term is also this same quantity, and it comes from the fact that the errors is the only thing that changes in our model. So if we have our beta 0 plus beta 1 times x. Now x changes, but it changes as a constant value. Recall that typically in simple linear regression we assume that the x values are known. So the only thing that is a random term here, or that has variance or covariance, is the error term. So the covariance of our y's is treated as the exact same as the covariance of the errors. Now the assumptions in matrix form. Again, we just discussed how this breakdown looks, but the assumption can be written as the vector of errors is distributed normally with a mean of a vector of zeros and a variance of sigma squared times the identity matrix, the n by n identity matrix. Again, 0 is going to be a 0 vector now, and I is that identity matrix. Note that because of the sigma squared in the diagonal elements, we can see that this is the assumption of equal variance. And the zeros in the off-diagonal elements indicate the assumption of independence. So for the least squares estimation, recall that in our previous least squares estimation, what we did is we wanted to minimize the error term. And so we had this error term. Recall that we took the error term, we summed the squares of the error term, took the derivative, and minimized. We still want to do this. That is, we still want to minimize this sums of squares of the error term. But now, for the sums of squares of the error term, what we're looking at is this epsilon transpose times epsilon. Now, if you want to think about this, epsilon transpose times epsilon, well, that's going to take each of these epsilon terms, multiply them by each of themselves, epsilon 1 times epsilon 1, epsilon 2 times epsilon 2, and add them up. So actually this scalar form, the sum of the errors squared, is the exact same thing that we get if we take the transpose of the error vector times the error vector. Looking at this using the replacement of what we have in terms of what our error vector represents, y minus x times beta, we want to minimize in terms of y's and betas, y minus x beta transpose times y minus x beta. This is kind of like a quadratic function, and again, you can think of this as it relates to the scalar term. When we take something transpose times itself, it's kind of like squaring it. So epsilon transpose times itself is kind of like squaring the epsilon terms and taking the sums of squares here. So this is kind of like that. You can think about that when we're looking at y minus x beta transpose times y minus x beta. It's not exactly y minus x beta squared, but it's kind of like that in terms of matrix form if you want to intuit it that way. Now we're going to take the derivative of this with respect to the beta vector. And using the chain rule, we can derive the derivative as negative 2 times x transpose times y minus x beta. So this is what our derivative then becomes. Now we want this to be equal to 0, which is a vector of zeros, and solve for beta. This results in what we call the normal equations, which is x transpose y equals x transpose x beta. Now solving this for beta, we multiply both sides by the inverse of x transpose x, and what we end up getting is that beta is x transpose x quantity inverse x transpose y. Now, this is a very, very, very important equation because this is the solution for our parameter estimates. Note that this is the solution for beta if we're using population level data, but we never do. So this is actually going to end up being the solution if we're using sample level X and sample level Y data for beta hat, or the B's, our parameter estimates in regression. Now, I want you to really, really think about this equation because this is so, so important. I'll go back to where it came from. This equation is so important because this equation does not depend or even indicate necessarily in the way that we've written it how many betas there are. In fact, this X transpose Y, X transpose X, this is a P by P dimension of from an earlier slide, we noted that X transpose X is a P by P matrix where P is the number of parameters. So this could be an arbitrarily large number of parameters, and this format is still the solution that we had. If you recall our previous solutions for the B values, we had B sub 0 as Y bar minus X bar times B sub 1, and B sub 1 was that sum of X minus X bar times Y minus, we had a whole big long equation for that. And then if we had gone on to B sub 2 and B sub 3 and B sub 4, if we had added more independent variables, the equations would have gotten even more complex. But in this particular case, because we've solved this with the matrix form, and because we've annotated or used matrices that are conformable out to as many dimensions as we want, including P, then this solution is broadly applicable. And again, this is very, very, very useful. If we find the design matrix, the transpose of the design matrix, and the Y vector, the vector of responses, with those three elements, we can calculate the parameter estimates by taking the transpose of the design matrix times itself, and then finding the inverse of that, and then taking the design matrix transpose times the Y vector, and then multiplying these quantities together. Literally, this gives us our parameter estimates for B. All right, so now we're about to go through some equations just to convince you that we haven't done anything really new or magical. We're just writing out some of the same formulas that we had previously. So recall that we had B1 as the sum of squares xy divided by the sum of squares x. And again, this was that sum x minus x bar, y minus y bar divided by sum x minus x bar squared. Then we have B0 as y bar minus B1 x bar. For the matrix format, first what I want to notice is what happens when I multiply these elements. So X transpose X ends up being a square matrix. Now X transpose X is a P by P matrix, but in the simple linear regression case, where we just have an intercept and a single independent variable, this ends up being in the top left. It ends up being the sum of X quantities squared in the bottom right, and then the off diagonal elements are just the sum of X. That's X transpose X. Now for the inverse of X transpose X, this is a little bit more complicated. We're not going to talk really through deriving this. It's not the worst thing in the world. But we do end up getting 1 divided by n times the sum of squares of X times the matrix with the sum of X squared in the top left, n in the top right, and then negative the sum of X in the off diagonal elements. Now the final element that we had in our calculation was X transpose Y. So X transpose Y, we're just taking all of these values and multiplying it by our Y vector. Recall that our column vector of Y's. Recall from our matrix multiplication that this is Y times 1, Y1 times 1, Y2 times 1, so on, Yn times 1, and then adding them all up. So the top is just going to be the sum of Y's, and then we have Y's times the X's, so the bottom is just going to be the sum of each of the X values times each of the Y values. Now we're going to plug these into the equation for B. So we start here and then we plug in those definitions that we just wrote out. So no need to panic quite yet. We're just plugging in those definitions we just worked out. Now when we take the next step, that is multiplying these components times this matrix. So we have for the top left, we take the sum of Y times the sum of X squared, and then we take the sum of X sub I minus the sum of xi, yi times the sum a negative sum of the x's, and we get that next component. For the bottom, the row, we get the sum of y's times the negative sum of x's. And then we have n times the sum of xi, yi. Oh my gosh, that was a mouthful. I butchered it terribly, but hopefully you can follow what we're doing here. It's a pretty simple matrix multiplication problem. If it's easier, just write A, B, C, D, and then E, F on your notes and just kind of write that out. A times E, B times F, adding them together and so on. It might be a little easier to see that way without all the summations and stuff getting in the way. All right, so now what can we do? Well, in this particular case, what we can do is we can distribute the divided by n in a couple areas, because this is going to give us the sum of y divided by n, which is y bar, and then the sum of x divided by n, which is x bar. Now, in a couple of these other cases, we're looking at these different components. We have the sum of, so in this case, the n divided by n is going to cancel out, and we're going to move that in front of the minus sign. So just flip-flop the placement of these two components, and then we're going to subtract the, now we have the sum of x, and if we have that divided by n inserted into here, that would be the x bar. To be able to write y bar, what we're going to do is use a mathematical trick, n divided by n. So y, sum of y divided by n, is going to be y bar, but then we have an extra times n, which is where this guy comes from. And again, feel free to work this out on your notes. Just following along with the verbal explanations can be a little tricky, but take some time. It should only take a couple minutes to work this out on your notes and convince yourself where these components are coming from. All right, so now we can identify that actually this bottom component is just the sum of squares of x, y. So that's kind of handy. In the top, we can go on and start breaking some of these different components apart into something that's going to be a little bit easier to look at in a second, specifically because we can break apart the y factors, as we'll talk about in just a moment. All right. So now that we've broken apart these y factors, and again, I mentioned we're going to talk about just now, what we can see is that we have y bar times n times the sum of squares of x, quantity squared, and then times x bar squared. So this is going to give us y times the sum of squares of x. We can then look at the sum of squares of xy times x bar by factoring out the different x bar components. So what we did here is just reorganize our information in a way that it's going to easily break down into these sum of squares of x and sum of squares of y components. Now, why did we do that? Well, why we did that is because we want to be able to organize and observe how these relate to our end goal of beta 0 and beta 1. And what I know is that if I have sum of squares of x divided by the, the sum of squares of xy divided by the sum of squares of x, then that's going to end up what's giving me my b1 in the first equation, and that's what we used in our equation to solve for b0. And actually, that's where we end up. We, after we've got this reorganization completed, divide the top and the bottom by sum of squares of x. The sum of squares of x cancels in the first term, just leaving us with y bar. Sum of squares of x, y divided by sum of squares of x is how we defined the estimate for beta 0 previously, times x. That is our equation for beta 0. For beta 1, the bottom of this matrix, the second row, is just the sum of squares of xy. So the sum of squares of xy divided by the sum of squares of x, that is what we had for our estimate of beta 1. So we've kind of demonstrated that this format of x transpose x quantity inverse times x transpose y works out to be our same parameter estimates that we got earlier. Now, what you'll note is that the format's a little bit different. Recall that we had two different equations that we solved. We kind of had b0 equals blank, blank, blank. Then on a different line in our work, we had b1 equals blank, blank, blank. Now these are going to come out as a vector. The first element of the vector is going to be the intercept, and the second element of the vector is going to be a slope when we use this matrix multiplication format. Be glad, actually, in previous versions of this course, this is a proof that you have to do on your own, demonstrating how we get from here to here. I guess we took it out in this class, but you can thank your lucky stars that you don't have to go through that one on your own. All right, so again, all that we're doing here is we're writing B0 and B1 in this fancy new matrix format. So why did we do this? Again, as we talked about before, the cool part is that the same approach works for a much broader dimension of matrices. Because our matrices are conformable in the way that we wrote them, we simply expand X to include as many independent variables as we want in the design matrix, then increase the vector B to represent the total number of parameters that we need to estimate, and then we can use the exact same formula. What that means is that this equation, y equals x beta plus epsilon, works for any number of independent variables. And in fact, this is our simple linear regression equation. This is our multiple linear regression equation. If I have 100 variables in my model, this is the same equation I use. And this is why people really like the matrix format, is I don't have to write out B0 plus B1 plus B2 plus B3 plus B4 plus B5 plus B6 plus B7 plus B8 plus B9 all the way out to 100 variables. If I have 100 variables in my model, I simply write it like this and indicate that this B vector is 100 elements long. All right, so now we can talk about the different fitted values. So recall that our fitted values y hat, we're going to now make a vector of these different y hats. So for each of the I observations, I have a predicted value. That predicted value was just B0 plus B1 times X. But just like we did before, we can break this down into a design matrix and the estimated, the parameter estimate vector. So we just have XB, or X beta hat, as our Y hat. Now, we also have a different way in which we can find the hat matrix. So the way that I just showed you is kind of an intuitive way that we can define it from our scalar forms. But because of this new definition, recall that B was X transpose X quantity inverse X transpose Y. We can sub that into our equation for finding Y hat. And actually what we end up is a matrix, this X times X transpose X quantity inverse times X transpose. So if I just move these parentheses to combine all these X terms together and then leave my Y term out in the end, I get this H matrix, which is sometimes called the hat matrix. Why we call this the hat matrix is this is the matrix that I can multiply by my vector of Y's to get my vector of Y hats. It's kind of interesting, and it can be useful in calculating, well, it can be useful in a lot of different ways, but specifically in calculating standard errors and identifying influential observations in some regression diagnostics. So it is a symmetric matrix. It's idempotent, which means that if I multiply the hat matrix by itself, I get that matrix back. It's kind of a weird and fun and unique property. It's not unique. It happens with some other things, but it's kind of a weird, fun, and interesting property, I should say. All right, so residuals. We've thus far been talking about the errors, but now that we have y hats, we can really calculate residuals. Recall that xb was our y hat, y was our response vector, so the residuals by our former definition is just y minus the y hats. Which is what we have always defined residuals as, except now these are vectors. This is a vector of all of my responses, and this is a vector of all of my predicted values. Looking at this, I can factor out the y on the right-hand side, and I end up with the identity matrix minus the hat matrix. So this is another representation, the identity matrix minus the hat matrix quantity times y, another formulation of the residuals. Now again, only the y is random in this. The x beta, nothing changes in x beta and randomly changes. The only random component that we have in our model is the epsilons. And we talked about this earlier, how the variance of y is just that constant sigma squared because of our assumption of constant variance times the identity matrix. The variance-covariance matrix for the residuals can be constructed from the hat matrix. So we just take the identity matrix minus the hat matrix quantity squared times sigma squared times I. But this just ends up being sigma squared times I minus the hat matrix, very similar to what we had before. And that's because our hat matrix is idempotent, and because the identity matrix times the hat matrix just gives us back the hat matrix. Now this is very useful in constructing the covariance matrix because the predicted covariance matrix, this is the theoretical value, sigma squared, but our predicted covariance matrix just uses the MSE instead of sigma squared to calculate the estimated covariance for the residuals. Now, because the vector b, this is our predicted parameters, is a linear combination of the elements of the vector y, we can look at the vector b as normally distributed variables because y is normally distributed. In fact, I think we had a homework problem where we went through this derivation in the scalar form. Now, even if normality is violated, the estimates tend to be normal. And I now that we've been in class a little bit, I can start saying things like this. Assumptions are kind of like shades of gray. You don't really, I mean, there are sometimes cutoffs. There's definitely statistical tests we can use, but they're shades of gray in that we are always violating normality a little bit. We're always violating linearity a little bit. We're always violating constant variance a little bit. So the question is, are we violating it enough such that our results and answers are being skewed such that they don't give us the information that we think that they do? So just like, again, looking at this like a shade of gray in the sense that if it's close to normal, then that tends to be normal enough. It's not about the statistical test. It's about, is it far enough off of this pattern such that I'm really concerned about it? When you get lots and lots and lots of data, and in fact, if we get to the chance later in this course, we may talk about big data. If not, we can look at taking some of our other courses, like the machine learning course. There's a couple different courses we talk about some bigger data in. But if we get to that point, you can look at calculating some of these values, especially normality and homogeneity of variance. And what you'll find is that the statistical tests virtually always show you a violation of normality, a violation of homogeneity variance. Very recently with a client, I was working with them. They had like 100,000 observations that we were looking at, and homogeneity of variance was hugely violated. Normality was hugely violated. I ended up pulling up a box plot of the two different options, and what I saw was that I couldn't actually distinguish which of the groups had a higher variance. So I was looking at these two groups. I did some density plots, some violin plots, some box plots, trying to figure this out, which of the groups had a higher variance. And I literally could not tell. What was happening is that the tests were so sensitive to such minor violations of the assumptions that I literally couldn't tell which one had a higher variance when I was looking at them. That is a fantastic case in point of why these are shades of gray, because that shade of gray was so close to being okay that I may as well not have worried about it, even though the statistic was indicating it was vastly statistically significantly different than what the assumption was. So in this case, again, that this idea that sometimes is misused is called robustness. It indicates that even if the assumption is violated, we don't have to worry about it. Many researchers use robustness because, frankly, they're too lazy to figure out what to do when assumptions are violated, and they use the concept of robustness even when there are drastic violations of the assumptions. That is not okay, and that's not what I'm trying to say here. My goal of what I would like to communicate here is that assumptions are never completely true. What we look at when we check assumptions is, are they violated to such a degree that they change the interpretation? And we don't shy away from saying that if that's going on. If they are violated in such a way that the interpretation of the statistic has changed, then we have to use a different statistic that doesn't change when the assumption is violated, in the case of normality, such as a non-parametric statistic. So to determine the variance-covariance matrix, we need to use a theorem. So in our theorem, suppose that U is a matrix is distributed as a normal, or excuse me, a vector that's distributed as a normal with a mean of mu and a standard deviation of capital sigma, or a variance-covariance matrix of capital sigma, and that V plus C, or V equals C plus du is a linear transformation of U where C is a vector, so we're just adding a vector, and D is a matrix, so we're multiplying this matrix times this vector U. Now all of this is to say that if I take a starting vector, I multiply it by a matrix D and add a constant C, then I know the distribution of the outcome. Let me say that one more time. If I start with a vector, I multiply it by something, then I add something to it. If the D is a conformal matrix and C can be added to it, then I know the distribution of it when it's done. So the distribution of it after I've added something and multiplied by something is that constant, whatever I added to it, plus d times the original mean of the vector, so mu, that original mean. And then the variance-covariance matrix, this one's kind of weird. The variance-covariance matrix is d, that matrix I multiplied, times the original variance-covariance matrix times the transpose of d. Now this one's kind of weird. We're not going to talk too in depth about this. We're just going to mention this as a theorem because it helps us to figure out what's going on with the variance-covariance matrix of the b's. And this is important because this is how we're going to perform our statistical tests. So recall that I can write my b's as x transpose x quantity inverse, x transpose y, and if I wanted to isolate the y, that's fine. So what I'm going to do is I say that this is y is my vector u that I was saying I know about, and I know the mean in this variance-covariance matrix for the vector y. And then this, all of this x stuff, this is going to be like that matrix D. So this is how we're going to make this work in terms of our betas, given that we know the distribution of the vector of y's. So now what we're going to do is we're going to apply the theorem to this vector of parameter estimates. And again, u is going to be this y vector. Mu is the mean of the y vector, x beta. Sigma is the variance-covariance matrix of the y vector, and we already know from our previous slides that sigma times the identity matrix. V is going to be the vector of parameter estimates. C is going to be the constant that we add, and we're not adding any constant. Note we had C plus D times U. This is D. This is going to be U. And then we're not adding anything to this, so this is just D times U. So that equation we looked at on the previous slide went a bit above and beyond what we're looking at. So in our case, C is just going to be 0. And again, D is this x, the quantities of x. Now the theorem tells us that the vector B is normally distributed. It tells us that the mean is this x transpose x quantity inverse x transpose times x beta. And if you think about this, x transpose x times x transpose x inverse, all of this ends up just being the identity matrix times beta, which just gives me beta. So the mean of the vector B is beta. Now this is what we mean by an unbiased statistical estimate, that the mean or expected value of our prediction or our predicted value is the hypothetical or idealistic theoretical value, the parameter. The mean of the statistic is the parameter. That's lack of statistical bias. And for the covariance matrix, this one's a little bit longer, but we can show that the covariance matrix turns out to be sigma squared times x transpose x quantity inverse. You can work this out from pieces of the text. We're not going to show this and worry about this, but it's really just rearranging some of these components in appropriate ways to be able to demonstrate that. Now, why is this important? So this is important because we use the variance of the statistic to calculate the standard errors, which in turn are used to calculate the statistical tests. So recall with the statistical tests, I needed to find the standard error to be able to know what to divide by to calculate the t-statistic. So if you go back to the very first time, I think it was lecture 3, where we talk about looking at the parameter estimates and standard errors, and we first talked about using statistical tests and creating confidence intervals, finding the standard error of B0 and the standard error of B1 was very important. This formula is how we find the standard error of B0 and B1. Of course, we use the MSE for the predicted value instead of this, which is written in terms of the population parameters. But this is, again, very important when we're calculating these components because they are what allow us to do the statistical tests. So some other variances and covariances that we've looked at. So we had the variance of the predicted mean, that was the MSE times, so in this case you can think of this as the predicted value we calculate the prediction interval, I guess is the right term. So the variance for the prediction interval. We also have the variance, this is the variance for the confidence interval. This one down below is the variance for the prediction interval. We showed both. And these are the matrix representations of both of those scalar equations that we discussed previously. Now, though, X transpose H is a row vector with just all of the X values listed out. So if I had multiple different X values, I would list them. Let's say the value of X1 is 35, and the value of X2 is 87, and the value of X3 is 52. I would just list those out in this row vector. In the case of simple linear regression, this is not a vector of X's. This is just a single X. So we have the vector 1 and then whatever our X value is. And that's what we would plug into X transpose sub H. Now we can also look at the sums of squares, and again, the sums of squares is an important quantity when we're calculating all of these different components, specifically in a regression table or an ANOVA table. ANOVA table is probably the biggest place we see these. The J matrix is important. It's just a square matrix, but unlike the identity matrix where everything was 0 and the diagonals were 1, in a J matrix, everything is 1. So this is what many students think the identity matrix should be, a matrix of 1s, and oh, doesn't that give me exactly what I had before? It doesn't. Nope. The identity matrix does that. This J matrix is a little bit more complicated, but in the J matrix, it's just a matrix, square matrix of 1s, and we'll just leave it there for this class. Sum of squares total is y transpose y minus 1 divided by n y transpose j y. The sum of squares of the error, now recall that that's just the error transpose times the error, can be written as y transpose y minus beta transpose x transpose y. And again, these should make sense, right? Sum of squares total is just how much of sums of squares are in y, and should be intuitively makes sense as to how we're calculating these. Sum of squares regression, this is going to be beta transpose x transpose y minus 1 divided by n y transpose j times y. Now we can also write these in what are called the quadratic forms using the hat matrix. I'm not going to focus too much about these. Actually, I'm just going to put these up on here and mention these, and then I'm going to leave them. The reason these are quadratic forms is they begin and end with y, so this is kind of like y squared, if you want to think about this with something in between the y sandwich. Again, I'm going to leave these and not really talk too much about them, but you can write these in those terms. So again, this has been quite a rush, I'm sure. The biggest thing I need you to take away from this is the standard error calculations, and recall that for the standard errors, it's actually going to be the diagonal elements of the standard errors of things like the standard error for beta that you're going to be using to calculate your standard errors. I think we showed in the notes the demonstration of the variance of the B terms. Recall that to calculate the standard errors, you need to take the square root of all of those, and that's probably going to be something that may come up on your homework. So you'll be using the square root of several of these variance calculations that we demonstrated, or at least showed the theoretical forms of here, to do those calculations that you'll eventually have to do for your homework. This said, you are going to be using software to do computations. I don't think we have any hand computations in class. I don't think you're going to have any hand computations in class. However, that does not excuse you from being able to understand what we're talking about when we talk about these quantities in matrix form. The quantities in matrix form and understanding the conversation, being able to follow it, are extremely important such that you can implement this in R. Because if you can't follow the conversation, if you don't know what's being calculated, then you're not actually going to be able to even type it into the computer, much less to follow an error check if something ends up going wrong. So it's really, really, really important that you follow along with what is going on, even if you don't necessarily understand the details of the hand computations. Again, that's not as important to me. What is more important is that you're following along with the form of the equations, the compatibility of the matrices as they're being multiplied, and getting the general idea of what's going on in our matrix forms and how it really does relate very, very closely with the scalar forms of the equations that we've already talked about. All right, so now that we have discussed simple linear regression in matrix form, and we have definitely alluded to including multiple parameters or multiple independent variables in the model, we are going to move on to multiple regression, which is a discussion of the multiple independent variables that we can put into the model. Simple linear regression has a single independent variable. Multiple regression has multiple independent variables. And frankly, in my view, this is where things start getting cool. I am really excited to talk with you about multiple regression because this is where our toolbox just explodes into a whole world of different options and things that we can take advantage of. So we will start that discussion next time, looking at the basics and kind of overviews of multiple regressions, all the different things that come into play. We'll do a few more of the matrix calculations as we talk about this in more detail. And then in the following chapter, after the next chapter, we will start to discuss a few more of the detailed elements in multiple regression. How we work through some of the more complicated pieces, but actually some of the more useful pieces of including data of different types as independent variables in a multiple regression model.